The mistake I made was I got these around the wrong way. So you make a mistake like that in line 2, the rest of your deduction goes straight. Alright, so from this you get this. So pre-multiply by y inverse on both sides, so you get y inverse x. The y inverse y cancel, so you're left with h1. And now inverse both sides. Okay. So you get y inverse x, all inverse gives you h1 inverse. Right. So remember when you inverse to the product. So AB inverse is just B inverse A inverse. Remember that? That's just from elementary group theory. Okay, so inverse this, so you'll get that inversed. Reversed, y inverse is self-inversed. So you get x inverse y, and that equals h1 inverse. Now look, this belongs to h, right? Because h1 belongs to h, and what is this? This is a member of big H. Big H is a subgroup, therefore it's a group. So the group will have inverses. So little h1 will have an inverse. So this, the inverse, belongs to the subgroup, belongs to the group, and therefore x minus x inverse y, because this is equal to that. Therefore, this belongs to your subgroup, right? And hence, if this is true, therefore this is true, and prove there, you've got it. There's your proof, right? Okay, and the last one, question 8, is you're asked to show that the following group is cyclic. So here's your group, so it's question 8. So you've got Z13, the non-zero elements of it. Binary operation is multiply. And so you have to show that this is a cyclic group by finding a generator. Okay, a generator. So just one would be enough. There might be more than one, but so if we can just find one generator. Now, what is this set? Well, it's non-zero, right? So we'll have 1, 2, 3, ... up to 12. Okay, and the binary operation is multiply. Well, one cannot be a generator, right? Because 1 squared is 1, 1 cubed is 1, 1 to the any power is integer power is 1. So that's not going to work. So let's try 2. We'll do this systematically until we find one. Right? So 2 to the naught, that's just 1. 2 to the 1, so it's 2. 2 to the 2, that's 4. So so far we're generating, they're all different. 2 to the 3, that's 8. 2 to the 4. 2 to the 4 is 16, but we're mod 13, so that'll be 3. Right? And 2 to the 5, that's that 32, mod 13. Is what? 2 13 is 26 and 6 left out, so that's 6. 2 to the 6th. What is that? 2, 4, 8, 16, 32, 64. 64. And 52, that's 4 13s. Difference of 12 returns, that's 12. right? Trust me, do it yourself. You'll get the whole set, right? Therefore, two is a generator, and as you get your increasing powers up to here, up until 12, so 2 to the 12th, and you'll get the full number of for all the members of your set here. Okay. Now, in fact, there are other generators for this group, but the question was just find up generator. There's a cyclic group by finding up generator. So one is sufficient. You've answered the question with just finding one, and fortunately it's 2. Otherwise, it could be a lot of work. I mean, imagine that there were only one generator and it was sort of on 11 or 12 or something. It might take you a while to find the thing. So finding a generator for a group can be tedious sometimes. It may require a lot of routine, boring work. Okay? Right, so that's the end of the problem-solving session. Now, next lecture will be on trying to find all possible types of groups, like cyclic, whatever, of groups of order up to 8, so 8 members, and it's quite detailed. A lot of detailed proofs. You have to sort of, as you branch down all the various possibilities, it gets quite detailed, and the branching gets quite bushy. A lot of possibilities. But that's we now have enough tools from this lecture, from chapter 14 or lecture 14. One lecture per chapter, one chapter per lecture. So especially the proof that the order of an element divides the order of the group. That particularly, which is sort of equivalent of Lagrange's theorem. That equivalence, that proof, if you like, is extremely useful for the next lecture. So I'll see you then. Ciao.